but it's okay.
If it's we can manage with this if that's okay for you.
Yeah, sure. Okay. So thank you very much, David. My name is Birhan Sefer, and on behalf of my colleague Nuria, I'm today to present the progress of this project supported by Vanitec in collaboration with SSAB. So I'm going to talk about the effect of vanadium carbides on the hydrogen embrittlement resistance of spot welded cold form high strength steels used in automotive applications. Let's see now. So a little bit about the background and the aim of this project. So basically advanced high strength steels with strength over 1500 megapascal can offer good properties or reduction in weight in automotive applications and CO2, lowering down the CO2 emission. However, their kind of drawback or sensitive point is that they are susceptible to hydrogen embrittlement. However, recent literature points out that if we have alloying with vanadium, then we could get some effective trapping of hydrogen in high-strength steels, providing possibility to kind of mitigate hydrogen embrittlement. On top of that, spot welding, it's a common technique to join automotive steels for automotive applications in body in white components. And the question here rises with if the spot welding can lead to changes or actually leading to changes to microstructure and also the vanadium carbides present in the material, and as well looking into the residual stress and how this can affect the trapping efficiency of the carbides and as well the hydrogen embrittlement performance or sensitivity. So in general, the aim of this project is to investigate the effect of vanadium on the microstructure and hydrogen embrittlement sensitivity of spot welded cold formed high strength steels used in automotive applications. So basically, there are three questions that we would like to address in this project. They are listed here. So the first one is related to the question whether additions of vanadium in the range of 0 to 0.3 weight percent can really influence the risk of hydrogen embrittlement of these kind of steels with high strength over 1500. Which the second is related to what is the effect of spot welding on the efficiency of vanadium on the hydrogen embrittlement resistance, and related to in context to changes in the microstructure, so vanadium carbides in general, or presence of residual stresses, and whether these are detrimental. And the third question is actually what is the effect of electrogalvanizing before spot welding, because electrogalvanizing process itself can introduce some hydrogen into the material during the manufacturing steps. So basically, these three questions I will try to answer at to a certain point at the end of the presentation today. Let's have a look on the project plan. So this was initially planned from the beginning of the project. So the project is ongoing in 3 phases, including phase 1 manufacturing, where the samples or the materials were manufactured in the lab scale. Then the second phase includes processing, so mainly electrogalvanizing and welding. And the phase 3 is including microstructural characterization and residual stress, as well as hydrogen embrittlement sensitivity. So far, the status is that work package 1, 2, and 3 are completed, and we are still working on work package 4, where we kind of still evaluate the embrittlement sensitivity. And there are planned 2 deliverables in this project, which one it's already done. It was a presentation, the conference in hydrogen steel conference in Ghent last year. And the second one hopefully will happen either by the end of this year or next year beginning. So let's have a look on the work package 1. This is just like to remind us, the participants or the new listeners, what we have did. So we basically did lab melts up to 2 kilos with 3 different materials: a reference material that doesn't contain vanadium, and two materials with a level of 0.15 and 0.30. And then we went through the entire processing step, like hot rolling, cold rolling, and then we used a Glibble to simulate the annealing steps. So the work package too, just to illustrate, so we did electrogalvanizing, or we used 2 different conditions of the materials in pickled sample to remove the oxide coming from the Glibble simulation, and as well as electrogalvanizing. And then on this slide as well, you could see the let's say the conditions that we used to spot weld the samples for the mechanical testing later on. So I have to say that this was a challenging step, because typically, according to standards for spot welding, we usually are used to quite larger samples. But here in this work, we managed to do spot welding on samples that are miniature compared to what is the standard recommending. And later on, I will show the results. It's still working, so we can do some classifications of the steels. So when it comes to the step of characterization of the microstructure and residual stress, so in this work package, we basically employ TEM, carbon replica method, to study the carbides. And then we have analyzed the carbides in non-welded conditions, so after processing or after getting in as-received state of the material. Of the materials, but as well in the welded zone and in the heat affected zone after spot welding. And the second part of this work package is related to characterization of the residual stress with XRD, that we did some preliminary measurements that I will show today. So let's start with the microstructural characterization. So this is just to illustrate that we indeed have carbides, or vanadium carbides, present in the vanadium added steels. So V15 and V30 refer to 0.15 and 0.30 weight percent. So you can see on the micrographs and also on the EDS pictures that the carbides are present. So this is the result for the carbides in non-welded materials, so as processed material, where we can see that the carbides basically have similar size regardless of the content. So they have about 11 nanometer size, while unfortunately we are not able to discuss about the number of density, but locally we could see that the higher amount of alloying with vanadium resulted in more numerous or more number of density compared to V15, for example. So the next is actually TEM results to compare what is happening during the spot welding process. So here on this corner you have an illustration from where we took the carbon replica. So basically we analyzed the center of the weld and close to the heat affected zone. So what we have observed is that we don't see any particles in the center of the weld. So most of the particles, vanadium carbides, were dissolved and they disappeared from the weld, but we could still see them in the heat affected zone. And when we look with the help of the scanning precision electron diffraction method, we could even distinguish whether we are talking about vanadium or titanium carbides. And in this particular case, we do see most of the carbides in the heat affected zone that are vanadium carbides, and the larger ones titanium carbides. So what can be concluded from this is that by the spot welding in the weld metal, we are dissolving the vanadium carbides, but we still can see some many number of carbides in the heat affected zone together with larger titanium carbides that are formed at high temperature. When we look in the V30 material, so what you saw previously was V15, less amount of vanadium. And now on this slide, you see the results for the V30. So this is only focused on the center. In the center, we could still see some large particles of carbides, as illustrated here on the TEM. So, but these carbides are having or had very complex chemistry. So, combined with titanium, vanadium, even chromium, and manganese, and so on. So our assumption is that these carbides are surviving the spot welding process in the V30, but not in the V15 material. And in comparison to that, I just want to stress that we didn't find any carbides in the center of the weld for the V15 alloy. Let's have a look on the heat affected zone. So this is for the V30 heat affected zone. We do see some vanadium carbides in the heat affected zone, similar as in V15 material. However, one interesting observation is that we see a lot of cementite here present in the heat affected zone, for which was not observed in the case of V15. So this is leading us to a case that we might have been not very careful in picking up the place from where we should comparably look into the both alloys to see the carbon replica. So we need to check this again. And one of the future tasks to do is maybe more simple, to do a detailed TCM analysis through the entire cross section of the weld, starting from the base, moving to the heat affected zone and the center, to see what kind of microstructure constituents we have present there in both V15 and V30, so we can confirm whether this is an artifact from the experimental work, or it's indeed a big difference in presence of these cementite particles. Okay, so that was about the TM characterization. So basically, what we can summarize up to now, we do see carbides in the production material, a larger number in V30, a number of density, but then spot welding is strongly affecting the carbides. In the weld zone, we basically dissolve them in the V15 material, while in V30 we could still see some larger particles and some less number of vanadium carbides, while in the heat affected zones still they're present in larger number. Let's have a look on preliminary results for the characterization of the residual stress now. So what we did is basically we perform a spot weld, and then we covered the entire spot weld with the clay, and then we start measuring the residual stress by help of XRD, starting from, let's say, at the interface between the heat affected zone or the outer diameter of the nugget, moving outwards towards the bulk. And these are the preliminary results that we got. So basically, when we are here close to the heat affected zone or the outer diameter of the nugget, and when we move towards the outside of the nugget, we see higher stress close to the nugget and lower stresses and gradually decreasing stresses as moving to the outer plane of the nugget. And in this sense, for example, for the reference material, which doesn't contain any carbides, the type of stresses were tensile, while for the V13, what we observed or we measured were compressive stresses. So this was a little bit suspicious for us, and then we tried to discuss this with our experts who do this kind of measurements, and then we came up with let's say some agreement that we expect that the distribution of stresses around the nugget in the nugget, so moving from the bulk or heat affected zone to the center of the nugget, should be let's say distributed on this way. So we should have some sort of compressive stresses out in the heat affected zone, while the stresses tend to be in tension or tensile as we approach to the center of the weld. So this indicates to us that we need to do a little bit more deep analysis, or maybe change the way of measuring it. And we have already discussed that we should measure it from starting from the bulk one side and moving in steps to the other side of the weld. So we cover most of the weld, so we can see what is actually affecting or what is the residual stress effect on the hydrogen embrittlement. Because at the moment we could not really say the difference between the reference and the V30 material. Okay, so that was about the work package 3. So now we're moving to work package 4, where we investigate the hydrogen embrittlement sensitivity. And to investigate that, we decided to perform 4 steps, or 4 sub work packages, where we evaluate the hydrogen trapping efficiency. That is done by charging the materials before and after spot welding with the conditions listed here, and then simply measure the hydrogen content with help of TDMS after charging and after resting of the samples at room temperature in air for some time. We have been performed that for before spot welding, and now we are in process of doing that for spot welded samples as well. So next step is to investigate the sensitivity, and that is using the mechanical degradation test or step load test, and that we already performed in all kind of variations of samples, non and spot welded, uncoated, and electrogalvanized, and I will show the results later on in these slides. Some fructography, which is ongoing, so I will show some preliminary results, and of course we want to see the effect of the step load testing or hydrogen uptake, which will be combined step load test with TDMS analysis to see how much diffusible hydrogen we have present in the material, or maybe deeply trapped, or correlate that to the trapping sites of the vanadium to verify why the failure is occurring. One thing that I should mention here, and it's important, is that the step loading test, we have been using different kind of approaches. First approach was that we use shared edges before the spot welding, so uncoated samples, because there we electrochemically charge the specimens, while we use polished edges for the spot welding samples to ensure that the hydrogen embrittlement cracking will occur in the weld, not at the edge of the specimen. So coming to the, let's say, first results for the trapping efficiency, here on these slides, you can see the effect of let's say, diffusible hydrogen loss. So we measure the hydrogen directly after charging, 1 and 3 hours after resting, or after charging and resting the samples at room temperature in the air. And here we have calculating the diffusible hydrogen loss based on these numbers. And basically, we could not resolve a big difference between vanadium 15 and 30 material, with the exception that, for example, after 3 hours, in the non-vanadium added steel, we have 93% of the diffusible hydrogen already effused out from the samples. Coming to the mechanical degradation tests, so here is a summary. So as I said, we have tested many conditions of these samples in uncoated or pickled, not spot welded. That's the blue one. Then it's the gray one, uncoated, pickled, spot welded, and then we have the same variations for the orange one and the yellow one in combination with electrogalvanized layer present. What we can observe from this chart is that we basically increase the time to fracture when we have an alloy that contains 0.30 weight% of vanadium, which leads us to conclusion that vanadium can be helpful in increasing the hydrogen embrittlement sensitivity. When we talk about which type of fractures we have, most of the fractures happened in the heat affected zone, as it's indicated here. So let's have a look. Let's have a look of the fracture surface, how it looks, for example, in uncoated non-spot welded samples and uncoated spot weld samples. So not spot welded, it's on the right, and on the left we have spot welded. And here you can see actually the average the time to fracture from 3 to 5 samples. What we could observe is that, for example, in the case of non-coated samples and non-spot welded samples, we have mainly ductile type of fracture with a lot of dimples, while in the spot welded we observe some brittle features and a lot of secondary cracks. When we look again on these effects, that is very important that I forget to mention is that beside what is critical for the loss of the time to fracture, or the increasing sensitivity of hydrogen embrittlement, it's actually electron galvanizing and spot welding together. So I'm coming to the summary of the work so far. I try to answer these 3 questions that I posed at the beginning of the presentation. So the first one related about the additions of vanadium. Could that decrease the risk for hydrogen embrittlement? And what we observe is that vanadium has a positive effect, and especially vanadium in contents of 0.30 weight % resulted in longer fracture time or time to fracture than 0.15, and compared to the reference that doesn't contain vanadium, both from the metal and welded joints. What was the effect, or what is the effect of spot welding on the efficiency of vanadium to the resistance? Spot welding, we see that it's decreasing the hydrogen embrittlement resistance, and this is most likely related to the differences in the microstructure that we need still to detail to analyze, and of course very likely to the dissolution of the carbides in the center of the weld and the presence of various other kind of microconstituents and carbides in the heat affected zone. So whether the changes or the other changes in the microstructure, are there any changes in the microstructure or presence in the residual stress in terms of spot welding? Yes, it was found that vanadium had similar size for both materials, but double in number for vanadium 30 as compared to vanadium 15 material. Carbides were found in the base metal heat affected zone, but not in the center of the weld for V15, for example. And the preliminary results for the residual stress analysis revealed that the stresses can be tensile and from tensile and compressive nature, but we need to verify this hypothesis that we have at the moment. And of course, the last question, what is the effect of the electron galvanizing before spot welding? So we saw, our results show that the electron galvanizing has decreased the resistance to hydrogen embrittlements for all materials and all conditions. And as a future work, what we have listed here is that we need to work a little bit on detailed microstructure analysis and additional fructography to understand details why there is a beneficial effect for vanadium 30 material compared to V15 and the reference material. To continue with some more planned and systematic study for the residual stress analysis to try to correlate that to the sensitivity as well. A combination of step load test with the TDMS testing to mainly focus on the reference materials, so no vanadium and V30, to clarify the let's say the better properties for hydrogen embrittlement in V30 material. And as I mentioned at the beginning, we plan to have another dissemination activity. We have not decided yet what it will be, but we will aim to be for a scientific publication. So thank you very much for your attention. That was all that I had prepared for this talk, and I'm looking forward for questions and comments.
Thank you very much for that, Burhan. It's good to see that vanadium's having a positive role in reducing hydrogen embrittlement. Any questions for Burhan on this presentation? Perhaps just a point of clarification for me, please. On your residual stress measurements, that sort of apparent difference between the V30 and the reference steel, that's you're not sure about that. That's going to be investigated. Is that correct?
Yes, that's true. That's true, because we were aiming. I mean, spot welding has been investigated earlier, and we know that the hardness varies through the, let's say, plane of the spot welded nugget, and then it's getting softer in the heat affected zone. But then we have been thinking that since most of the cracking occurs at the heat affected zone, so we were thinking to take only residual stress measurements in that regions, but apparently that's not enough, because we ended up in maybe hitting different regions for the different samples, and we show that we have different even nature of the stresses. So we need to clarify that a little bit more.
Yeah. Okay. Yeah. Fine. Thank you. Any other questions on this presentation? Okay. Well, thank you very much for that. I think we'll call it a halt there on that presentation. So thanks very much, Burhan.
Thank you.
I built a 10-minute break into the agenda at this point, and we're slightly